We would like to welcome you and thank you for joining us for this installment of the Groundwater Foundation's webinar series, co-sponsored by the Water Research Foundation. In order to achieve the Groundwater Foundation's mission of educating people and inspiring action to ensure sustainable, clean groundwater for future generations, the Groundwater Foundation is offering these webinars. This is our second one in 2010. While we'll continue to offer some conferences, seminars, and workshops, we feel the webinar series offers us the opportunity to provide valuable resources to you at a minimal cost and no travel expenses. My name is Brian Reitz. I'm a program coordinator at the Groundwater Foundation, and I'll be hosting today's Groundwater Foundation webinar, Emerging Contaminants in the Environment. I just wanted to walk you through a feature that we'll be using during the course of today's event. It's the chat feature. If you would like to ask questions of me or the presenter during the course of the webinar, please type your question into the chat box just to the left of the send button in the bottom right-hand section. I will monitor the questions throughout the presentation, and then we will address as many of these as possible during the Q&A segment at the end of the presentation. Today's topic is emerging contaminants in the environment with Dana Kolpin. Dana is a research hydrologist for the U.S. Geological Survey in Iowa City, Iowa. He received his bachelor's degree from Iowa State University and his master's from the University of Iowa, both in geology. His research interests include the fate and transport of pesticides, pharmaceuticals, and other emerging contaminants in the environment. He has published over 100 papers and reports on environmental contaminants. He has been the project chief of the USGS Toxic Program's Emerging Contaminants Project since its inception in 1998. So I want to welcome you, Dana.
Thanks, Brian. Yeah, I thought I would just kind of today go over some of the research we've been conducting as part of the ongoing investigation that Brian mentioned that's been funded through the Toxics Program. I'll touch on a few things that maybe you've heard before, but I really wanted to focus on a couple of papers we published over the past couple of months. But just as kind of a quick introduction, I think most of you probably are aware of the topic of emerging contaminants, but certainly just to note that we have become a very chemically dependent society, and certainly many thousands of chemicals are used in our daily lives. And all these contaminants have the potential to become environmental contaminants. So really, I think one of the things that really kind of captured the public's attention, particularly the past couple of years, is this kind of water cycle that I'm displaying here. Certainly, we're using and ingesting many types of compounds, both liquids and pharmaceuticals. We're also using other types of compounds that can be washed down the sink or in the toilet. And really, it's that potential to then be discharged through the wastewater treatment plant into the streams, and then potentially everybody lives downstream of somebody else. That wastewater treatment plant outfall can be upstream of someone else's drinking water intake. So I think that's certainly, there's many other types of pathways, but this is one that has certainly captured the public's attention. And certainly, I think it was in 2008, a couple of years ago, AP had a series of stories on pharmaceuticals in drinking water, and I think that ratcheted up at least the education and awareness that these contaminants are in the environment and have the potential for exposure, certainly via drinking water and other pathways as well. Even though we were finding these results several years before that, the stories were very good at raising the awareness of this topic. And certainly emerging contaminant research has really picked up in speed. Since 1998, certainly there's papers that go back even into the 70s that talked about pharmaceuticals as environmental contaminants, but really took the mid-90s when the new tools, analytical tools, were available to measure these types of contaminants to the very sensitive levels that are needed, is when we really started thinking about these contaminants, these emerging compounds as environmental contaminants. And certainly since, say, the late 1990s, early 2000s, really that growth and number of research has picked up dramatically. And this is just showing the number of publications in about 6 to 8 target journals. So this certainly doesn't represent all the potential publications, but shows the same trend as with that exponential increase, and certainly has been no sign of the number of research tailing off or leveling off as yet. There's more and more people and researchers getting into this fast-growing topic. And this just kind of shows, at least in my mind, the fundamental research questions relating to pharmaceuticals and emerging contaminants in general. Certainly, are these compounds entering our environment? What are the sources and signatures from the various sources of potential contamination? What happens to these compounds once they enter the environment? Do they degrade? Do they absorb, transform into other contaminants? Is there adverse ecological health effects? And there's adverse human health effects from being exposed to these compounds. And finally, what can we do to minimize their environment, their entry to the environment, or remove them before they get into the environment? Those that I've kind of circled in yellow kind of fall under the USGS mission of this type of research. And now I would say that this human health aspect we haven't gotten into yet, certainly is on our radar screen, but we haven't touched base on that type of research yet. But certainly this top 4 bullets is something we've been investigating quite heavily over the past decade. And this kind of just shows our organizational structure for the projects I'm talking about that I've been project chief on over the past 10, 12 years. Certainly early on, we're very heavy in terms of here's a new method, and let's look at are these compounds in the environment. So our early foray was certainly methods development and occurrence. But we very quickly evolved into this much more holistic source to receptor research. We looked at all these other aspects that are shown here. And just quickly in terms of, how do we figure out what compounds we should be looking at? As I mentioned, there's many thousands and thousands of possibilities, particularly when you start adding transformation products into the mix. But certainly we look at environmental occurrence. What have others found in terms of compounds in the environment? What do look at the chemical and physical properties? Do they look like they're persistent enough to once they get into the environment to be transported? We look at use in terms of either number of prescriptions or mass manufactured. Any research on toxicity, although this is very limited for many of the compounds that we're talking about, but as people start showing effects, it certainly helps our prioritization as we continue to develop new compounds or methods for new compounds, the pathways into the environment, and certainly stakeholder input as well. And as always, there's always surprises where things we would never anticipated, but we in fact find in the environment. So that always is part of the equation as well. Very quickly, just kind of show how our capabilities have evolved through time. Back in 2000, we had a couple of methods. This is specifically to pharmaceuticals. I thought this would be a nice frame of reference, but really the same patterns hold true for emerging contaminants in general. Back in 2000, we had a couple of methods, LC and GCMS, and we can measure about 47 pharmaceuticals. Now, 10 years later, we're looking at much more sophisticated methodology. Now the gold standard is LCMS-MS and GCMS-MS. We have better tools, more methods, and we can measure about triple the number of compounds in water. And now we're getting into solids as well, and solids include soils, biosolids, bed sediment, etc. And we do have now methods for tissue as well. So it just shows that even though we're still scratching the surface on terms of the potential compounds we could be looking at least what we can look at is growing, and hopefully as we continue to develop methods, we're looking at those that have the highest priority, because this is an expensive and time-consuming process. So I don't want to get into the next section real deep. You may have heard some of this information before, but in terms of that first fundamental question, are emerging contaminants entering the environment? I think everybody would understand at this point that yes, they are. They're present in groundwater and streams, generally at low concentrations, although not always the case. Certainly as a whole, streams and surface water tend to have more compounds detected at higher concentrations compared to groundwater. but many of these compounds are mobile and persistent enough to become a groundwater issue. And really, it's that mixture issue which is, I think, more of a surprise. It's not so much of a surprise that we're finding these compounds, but generally when we find a compound, it's that very complex soup of a whole number of compounds from a whole category of classes. And these compounds are entering via both human and animal pathways. And really the other point I wanted to get into before I get into our more recent papers is certainly we do not want to just focus on water. Early on that was the focus of looking at, for streams, for example, look at just the water in the streams. That's partly due to the methodologies. Water tend to be a little less complicated than developing methods for sediment. But as we can see here, this is a list of compounds. The compounds themselves is not so important. This is a range of pharmaceuticals, but it's the pattern in the blue and red bars. When we look just like looking at water, yeah, there is a few compounds that are primarily found in the water phase, but there's also a number of compounds that are primarily found in the sediment phase, with several that are fairly prevalent both in water and sediment. So if we just would look at water in streams, for example, we would be underestimating both environmental occurrence, but also potential environmental exposures. So I don't want to get into all the potential sources, but certainly here's a list of at least some of them. It isn't all inclusive, but it does include a range of both human and livestock or animal type sources. I would say wastewater treatment plants are those that have received the most attention, but there's a whole range of other potential sources that are starting to be looked at and have been looked at more recently. And again, kind of focus a little bit more on pharmaceuticals. This is a little more complex diagram of potential sources and pathways for pharmaceuticals. I would say that most of the effort up to this point has been kind of at the consumption or purchasing stage, but in reality, if you back up the pipe, so to speak, that potential pathway into the environment goes all the way back to the production stage. And there has been a paper just a couple of years ago that dealt specifically with a wastewater treatment plant that did receive pharmaceutical manufacturing, in this case quite a bit, where there was 90 bulk drug manufacturers inputting into this wastewater treatment plant in India, and they really had, I would say, astronomically high concentrations in the treated effluent. This is not influent, this is treated effluent. So really, 28,000 micrograms per liter, which is just huge. So that kind of opened our eyes in terms of thinking about, are these same types of sources taking place in the U.S.? And as we were starting to develop this particular study, others were actually telling us that really this would be a waste of time, and their assumption was that, first of all, pharmaceutical manufacturing is highly regulated, so they wouldn't be releasing active ingredients into the wastewater treatment plant, and why would they dispose of valuable product that has an inherent value? But in reality, there's really few data to show that these assumptions are valid, and certainly that study in India shows that at least that is, hypothetically, is possible that the same type of situation could be taking place in the U.S. So we did move forward with this study. Pat Phillips was instrumental. He is in our New York Water Science Center in the state of New York, and we're having some early samples from several wastewater treatment plants in New York, where as the effluent samples are coming in, the chemists were noting very high peaks in unknowns. And so they looked at the chromatographic library and were tentatively identifying a number of pharmaceuticals that we hadn't been looking at up to this point. And then with these tentatively identified compounds, we were able to obtain standards to really develop a quantitative method so we can move forward with really definitively looking at this type of source. So in terms of a network design, we selected 23 wastewater treatment plants that were sampled once, and these were meant to be representative of more typical effluent from across the country. And then we had 3 plants, wastewater treatment plants in New York that were sampled, heavily sampled, almost about 40 times, with 2 of these plants receiving pharmaceutical manufacturing input. With these 2 plants that received the PMF or pharmaceutical manufacturing input received about 20% of the inflow was from this in particular industry. So starting off with the kind of the line or the national study. Again, here's the 7 compounds that we identified, and these were really new compounds for us, and in reality have really haven't looked at anywhere worldwide. There's some limited amount of data, but really these compounds have not been looked at with any detail. Again, these 23 plants were all sampled once, and kind of the general rule of thumb is for effluent, for pharmaceutical concentrations in effluent, you should rarely exceed 1 microgram per liter or 1 per prevalent, and you might have a few occurrences, but certainly not exceeding 10 micrograms per liter. So you can see for these 22 plants, that was indeed the case that none of the concentrations exceeded that 1 microgram per liter rule of thumb. Now, we did have some compounds that were very frequently detected. Butalbital, which is barbiturate, was found in almost every effluent, and then a couple other of these compounds were found in about half the effluent sample. So we did have quite a few detections, but again, no detections were above 1 microgram per liter. Now, for in essence of time, now from here on, I'm summing all these 7 compounds into a total concentration. So again, for these 23 sites, now I divided those 23 sites into sites that had no hospital input versus those that had hospital input. Again, even when you add all the 7 up into a total concentration, you had some that maybe just grazed the 1 microgram per liter limit, but essentially all the compounds concentrations were still below 1 microgram per liter, even when you total all of them up into a single total concentration. And really saw no difference between wastewater treatment plants that had hospital input versus no hospital input. Now, when we look at the 3 wastewater treatment plants in New York that we sampled very heavily, pushing 40 samples per plant. Again, New York 1 is the site where we had no PMF input, and you can see this site really matched up almost identically with kind of a national baseline network. Just concentrations just squeaking above 1, but for the most part, all the total concentrations were below 1 microgram per liter. Now, when you get into the other 2 New York plants that did have PMF input, now you can see a totally different story, where New York 2 had median concentrations in the tens of micrograms per liter, and New York 3 actually had median concentrations in the hundreds of micrograms per liter, with some concentrations exceeding 1,000. And now, with our continued sampling, we had maximum single concentrations in around 3,000 to 4,000 micrograms per liter. So certainly wasn't in the 20,000 to 30,000 micrograms per liter that was found in India, but certainly it was 1,000-fold higher than what most would expect to be as typical concentration. So this, for the first time, really showed that pharmaceutical manufacturing can, in fact, be a potential source of pharmaceuticals to the environment in the U.S. We are now following up with additional studies of these 3 plants themselves, looking at specifically antidepressants, again, resampling effluent, but are now collecting samples of biosolids, because if we're finding hundreds of thousands of micrograms per liter in the effluent, many pharmaceuticals actually get concentrated in the biosolids. We could even find higher concentrations in the biosolids that then are applied to the land surface as a source of nutrients. We're looking at, again, stream water downstream to see, with the dilutional component, are we still seeing much higher concentrations in the associated stream samples, looking at bed sediment, and we're even collecting fish to look at tissue concentrations. And on a national scale, we're in the midst of developing a national scale study to see how prevalent these high concentrations are, in fact, in the U.S. Did we maybe just capture the high end of the spectrum with these compounds, with these sites, or is this somewhat typical of sites that do receive pharmaceutical manufacturing input? This kind of goes back to a previous study. Just to, again, I want to highlight the fact that biosolids are a very important pathway to the environment. A lot of the research to this point has been on effluent, but I would say over the past 5 years, people are beginning to understand that a lot of times the removal in a wastewater treatment plant is not removal in the sense of degradation of these compounds or mineralization of these compounds in the treatment process, but it's just a matter of concentration or partitioning of these compounds from the liquid phase to the solid phase. And you can see, in fact, this paper was published in 2006 that a range of number of compounds were found. Certainly found pharmaceuticals, but some of these other types of emerging contaminants were 2 to 3 orders of magnitude higher in concentrations in the biosolids. So again, we're not saying that this is necessarily a detriment or have a negative effect to the environment, but certainly understanding that these compounds can be quite high in the biosolids. We just need to understand, is there any consequences to them having these compounds present and using biosolids and sludge as applied to crops and plants as a source of nutrients. We're doing a range of transport and fate research. I won't have time to get into all of them, but I did want to touch base on, again, one of the research aspects that we published of late. We have two streams that we've studied fairly intensively, one in Iowa and one in Colorado. Both are effluent impacted systems, which means they're basically have wastewater treatment plant discharge, and at times can have a significant amount of flow being derived from the effluent discharge. We had a number of background data to know that there is ECs present in these streams, so we can then look at their fate transport after their input into the surface water bodies. These are relatively small basins, so we're trying to keep things as simplistic as possible. Every basin is complicated, but there's no sense going to very massive basins with lots of sources and very complex hydrology. Again, we do have a basic understanding of the flow system to help us interpret the data. There's controls above both these wastewater treatment plants, which really wasn't a design criteria, but when we get into the fish aspect, I'll talk about in a minute. These low-head dams are very helpful to be able to look at fish populations above and below the wastewater treatment plant. So this barrier to flow really helps us get a better confidence level that we are truly looking at two different fish populations. And both these wastewater treatment plants are undergoing major changes. I'm not really going to get into that today, but the Boulder wastewater treatment plant is already ongoing a transition and upgrade from a trickling filter to an activated sludge. So we're comparing and contrasting before and after that upgrade. And just as interesting, Fourmile Creek is actually the wastewater treatment plant discharging to this creek is going to go offline in a year or two. So we'll have an opportunity to totally shut off the source and see how the system reacts then to that faucet being turned off. So before we actually do our sampling with these effluent impacted streams, it's very critical that we know the timing of how long it takes for water to move from point A to point B. In many natural streams, you can use more synoptic type sampling where you can just go out and during kind of stable base flow conditions, things are at equilibrium. You can do a quick sampling without really taking time and travel into account. But with these types of streams, the wastewater treatment plants are continually pulsing, so you really don't get stable flow conditions, particularly at these lower flow conditions. So it's important that you do, in this case, what we did is inject rhodamine dye. So we got a variance from the state to do so. This is a harmless dye, fluorescent dye. So then we can follow that dye plume as it moves downstream, and then we know how long it takes for water to move from point A to point B. And certainly this particular study did capture people's attention, and we did get a little write-up in Time magazine as we were conducting the early phases of the study. And this shows us this rhodamine is very cool stuff. This is very close downstream for where we injected the dye, and it's for when you look at water quality, a lot of times you can't see the contaminants, so we don't have a lot of visuals, and this rhodamine really is one opportunity for us really to get some visualization of what's going on. So for the study I'm talking about, for these particular streams, we looked at antidepressants specifically, and there's a whole range of different antidepressants from SSRIs and so forth. But the main point is a lot of these antidepressants are now some of the most highly prescribed pharmaceuticals in the U.S. So we developed methods. We looked at effluent, started looking at effluent. Again, here's the two streams we focused on, but we have another effluent in Texas where we basically, one of our first initial findings was that the compounds, antidepressants that are typically were being looked at up to that point in time, fluoxetine, which is Prozac, sertraline. These are a couple of decadents of fluoxetine and sertraline. These compounds are not, in fact, the compounds that are found in the highest concentrations in the effluent. This is consistent amongst all the effluents we looked at, where, in fact, it was particularly venlafaxine, which is found far and away more than any other of the antidepressants we looked at. But these big three really hadn't been looked at up to this point. So that was one of our early findings, is there's a whole range of antidepressants that hadn't been looked at that should be looked at because these are the compounds that are being found in the highest concentrations in the effluent. We're looking at Fourmile Creek now. Again, we have the effluent. Again, have that same trend of the big three. But now we're looking at in the stream itself. Here in this case, we're looking at roughly 3 kilometers downstream. And this last column, we're looking at 8 kilometers downstream. And you can see between the effluent and that first sampling point downstream, you do consistently have a decrease. And primarily, this decrease is due to dilution. We didn't have any detections of antidepressants in the upstream water above the wastewater treatment outfall. So really, it's that mixing of the clean water with the effluent is what's causing all this decreasing in concentrations. But even when you get as far as 8 kilometers downstream, now the compounds I highlighted in yellow, these compounds were had statistical lower concentrations, but a number of the other ones were within analytical variability. So really, a lot of these compounds were moving relatively unchanged in a conservative fashion, at least through this 8-kilometer reach. And even those that were having some changes, whether that was due to absorption or degradation, we don't know at this point, were still detected 8 kilometers downstream of the outfall. But we looked at more than just the water, and we really thought it was important to look at other hydrologic compartments as well. So as long as we were out here, we again mentioned that Lowhead Dam upstream of both these sites, so we did electroshocking and collected fish, and we selected white sucker because these are native fish to both Boulder and Fourmile Creek. After the collection, we did some fish health assessment of the fish in general, but we also removed their brains to see what we could find in terms of antidepressants in the neural tissue, as these compounds are specifically designed to have an impact on neural tissue. We were curious to see if we could find antidepressants in fish that will be exposed to this water. So this is Boulder Creek. Again, this is a little complicated graph. On the y-axis, it's not concentrations. This is a normalized concentration for each of these matrices. So basically, the highest compound in each of the matrices is normalized by the highest concentration, compound at the highest concentration. So it shows for water, again, it's the big three of venlafaxine, which is normalized. So that has the 1 on this axis, and you can see bupropion and citalopram, as I showed in the previous graphs. Those are the compounds were found in the highest concentrations in water for Boulder Creek. Now we start looking at other compartments. We see sediment in the green bars here again. Venlafaxine is still the highest compound found in the sediment. The sediment was a little bit different in terms of there was more compounds being detected at higher concentrations. So it wasn't really just the big three. It was venlafaxine and a number of other compounds. But the big, I think one of the big findings was when we looked at fish, yes, we found antidepressants in the fish, but what we found most frequently in the water and sediment was not what we found most frequently in the fish tissue. We did find a range of compounds. It was a couple of these degradates, norfloxacin and norsertraline, and some parent compounds, floxacin and sertraline, were in fact the highest concentrations. We don't know what this means to fish. We don't know why these compounds had higher concentrations in the tissue relative to the other compounds, but that is what we found. And the same was true with Fourmile Creek. And unfortunately, the sediment we collected in Fourmile Creek, the chemists had issues with the analysis, so we just have water and fish brain data for Fourmile Creek. But again, we had that same trend of venlafaxine being found in the water just below the wastewater treatment outfall and 8 kilometers downstream. But when we looked at the fish immediately below and 8 kilometers downstream, again, we had a much different profile. And that profile really was similar whether you were immediately below the outfall or a fair distance below the outfall. So again, we don't know what this means to the fish. Certainly there's been studies now that looked at these same antidepressants and at similar concentrations, so at environmentally relevant concentrations. I have seen papers that show that a white sucker, fatty minnows, for example, their escape mechanism for avoiding predators, because they kind of bend into a C and then burst away from predators, that their behavioral pattern is shifted where they have a slower reaction to predators. And also seen papers that shown that shrimp actually have a different swimming behavior as well, where they tend to be in a light more after being exposed to these compounds, and that can increase their potential predation. So even though these compounds may not be killing aquatic organisms, if they're affecting their ability to react to predators, it still could have a significant impact on their population levels and their ability to reproduce. So kind of shifting then, as we're talking about these compounds and finding the fish, there is one study I did want to talk about as a case study of endocrine disruption. Again, this is Boulder Creek, again, one of those streams that we looked at more intensively. Here shows the 17-beta estradiol. This is a natural estrogen that all humans excrete. And again, you can kind of see the same pattern we've seen with these kind of effluent impacted systems, where above the wastewater treatment plant, it's generally low or below our ability to measure. Much higher concentrations in the effluent and immediately below the effluent discharge. And you get some attenuation downstream, but still, even again, this is roughly 6 to 8 kilometers downstream, still seeing significant concentrations with distance below the wastewater treatment plant. And just to show here, we're looking at, again, got the above the wastewater treatment plant, the effluent itself, and the site immediately below the discharge point. Again, we got two different points. The main thing I want to show from this slide is that one-time sampling isn't necessarily representative of what you're going to find at other times of the year. So we have two different samplings. You can see this is total estrogen equivalence. We saw that the spring 2005 had a much higher estrogen equivalent than the fall 2003. And the stack bars show that it's not just a single compound that could be causing that estrogenicity. It's generally that mixture that I mentioned previously. So it really shows the complicated nature of the situation. Now, as it turned out, the University of Colorado was looking at the same stretch of Boulder Creek, looking at effects to native white sucker. So it was very fortuitous that we initially were working independently and then realized we were both working in the same system and started to work jointly. The early work showed, looking at white sucker above and below the wastewater treatment plant discharge, you can see upstream they had none of the male white sucker had intersex, which basically male fish that have both female and male characteristics, and roughly a 50-50 distribution of male to females. Where downstream, about 20% of the males were in fact intersex, and there were fewer males to start with. There was a skewed sex ratio, more females to males. So to look at this problem to see, okay, we know there's compounds in the water that are endocrine disrupting. We don't know if they're causing the observances of what was happening in the white sucker. But so we were seeing strange things with the white sucker. We were seeing compounds that could cause endocrine disruption, but really didn't have that cause and effect link yet. So the approach we took was really to deploy a laboratory on site, so we could basically capture the natural availability. We're basically continually pumping water into these two tanks. One is effluent and one is the control water upstream, bringing them to temperature, basically to equilibrium, to equal temperature, because cold water and warm water could have different effects to the fish. So we're capturing the natural availability that can happen in the stream itself in terms of the chemistry, but in a controlled laboratory setting. So hopefully then we can better tease out, is there impacts from exposure to these types of compounds. So we did these exposure experiments, again, with male fatheads, and we found, in fact, that when you expose male fatheads to effluent, that we saw very quickly increases in vitellogenin. Vitellogenin is a female egg yolk protein that should not be present in males, at least not in an elevated level. So we see very quickly that internally these male fatheads were starting to look like females. And we also found, I think even more surprisingly, male fatheads have these nuptial tubercles. These are kind of secondary sexual characteristics that after exposure to effluent, these male fish were starting to externally look like females. And so then the question is, if they are looking like females, are they acting like females, where the males have a very strong characteristic of guarding the nest after exposure to effluent, or is that nest guarding behavior pattern being decreased and starting to act like females as well? So that's what the ongoing research is now looking at, to see what impacts there is. And interesting enough, I think this paper isn't quite published. It's in journal review, but some of our latest research, as I mentioned, Boulder Creek has now shifted from trickling filter to activated sludge. These early exposure experiments were still during the trickling filter stage. Now that we're repeating these experiments in the activated sludge, we're seeing that there is a definite improvement where we're not seeing this quick and dramatic feminization as we saw earlier. So that's certainly very good news. So with that, I know I went through this fairly quickly. Certainly want to acknowledge the very broad team that we have. We're multidisciplinary. We're spread all across the country. We're a mix of hydrologists, chemists, biologists, microbiologists. So I think we have a very strong team, and certainly put us against anybody across the world. I think we're doing certainly world-class research. I do want to highlight our website. We have a complete bibliography is on this website. I try to keep this updated roughly 2 or 3 times a year. We currently have pushing 200, certainly more than 200 publications that we published to date. So I would encourage you to look at this website, and you'll not only see the papers I talked about today, but all the other papers that we published. I just didn't have time to cover in this short website. So again, here's our website, and if there's time, I will certainly field any questions. Thank you very much.
All right. And now's the time for some questions that we did receive some during the presentation, but if you have additional questions, you can ask them through the chat feature now as well. A reminder that you need to type in the bottom section just to the left of the send button in the right-hand panel there. Well, the first question is, Dean, if you want to go back to slide 19.
Okay.
Someone had a question as, what does carbon normalized mean there?
Yeah, since I'm not a chemist, I'm a hydrologist, but I think that's because each biosolid can have various amounts of carbon, and carbon, a lot of compounds like to absorb to carbon. At least that's my interpretation. So this is normalized. So each of the biosolids are carbon normalized. So they're more of a apples-to-apples comparison between the 9 biosolids that were analyzed for the study.
Okay. If you want to switch back now to your final slides, that would have your email up there for people. People know that too. So another question is the difference between USGS and US EPA analytical methods for EC.
I would say they're probably somewhat similar, particularly with time. We're collaborating more and more with EPA. I know they have used our early methods because we had published methods probably in advance of some of their early work, but I suspect that they have fine-tuned and maybe branched off a bit on their own as well. I haven't looked at their side-by-side comparison. I certainly think there's a number of compounds were overlapping, but I would suspect, particularly with our latest research where we're now, as I mentioned, we're pushing 150-some pharmaceuticals, I suspect that we now are looking at a number of compounds. They aren't, but there may be vice versa. There might be a few compounds that they deemed as high priority that just haven't hit our list as well. But I think the basic premise, particularly for pharmaceuticals, most people are using LC-MS as the method of choice to look for these compounds because that gives you the specificity and sensitivity that you really need for looking at these compounds, which are not easy to isolate from water and other environmental matrices.
Right. What's the source of the 1 UGL rule of thumb?
I think there's no written law to that, but that's as we've kind of looked at F1 in general. I think the scientific community in general has kind of saw that by far most of the concentrations were in the sub-part per billion range. So that's just kind of a rule of thumb where as the growing amount of data from F1 is being published and generated, not that you can't see concentrations, but generally most certainly were less than a part per billion and even more commonly, certainly less than 10 part per billion. So when we started seeing hundreds to thousands of micrograms per liter in F1, that is certainly far and above that anybody has seen, with the exception of that study in India where they really had tens of thousands of micrograms per liter.
Another question, do you know if there are any regulations underway to address the effluents being released by the pharmaceutical companies, or should there be?
I'm not aware at the moment. Certainly the paper we published a couple months ago, I think, raised the awareness that, there's nobody's out of compliance by discharging, their waste from a pharmaceutical manufacturing plant into a wastewater treatment plant. That's nothing that's illegal at the moment. But I think as EPA, sees our data, I think they may I can't speak for them, but they may reevaluate, what's going on, and if in fact there does need to be some changes taking place. Again, they may wait and see if we just happen to capture some anomalous sites, or if it's something that's more commonplace, and that's something that ongoing research will hopefully play out in terms of how prevalent are these high concentrations, and if something needs to change in terms of preventing these big pulses coming into a wastewater treatment plant.
What research is available on water treatment removal for emerging contaminants, and what works best?
I think there's more and more of this type of research going on. Certainly, what we found in others as well is the trickling filter generally is less efficient at decreasing concentrations in effluent. That's something we have found and others have found and published as well. Something that we just published with WRF, and if you contact me, I don't have the information at my fingertips, but we just published about a 200-page document looking at hormones and other emerging contaminants in a subset of about 4 wastewater treatment plants, and we tried as best we could to do a mass balance looking at influent, effluent, influent biosolids, and really trying to figure out, is there true removal? Is it simply partitioning into the biosolids? And that type of research is really, I think there's a growing number of people are looking at treatment, because certainly, that's one thing we do want to minimize. Concentrations go into the environment, so that's one angle of trying to figure out which treatment is best at removing, and is there upgrades potentially going to be required. But I think all that is kind of in the early stages. We certainly don't want to start having all these plants just spend millions of dollars to upgrade and find out there's little to no cost benefit, because that is expensive. There is an energy aspect as well. So that's certainly one aspect of this whole research.
Another question says, Boulder had the trickling filter solids contact process, not a conventional trickling filter process. Are you seeing large differences with their current activated sludge effluent?
Certainly, as I noted, we haven't published the data yet, but the results, at least in terms of the fish exposures, we are not seeing the dramatic feminization that we saw earlier. I haven't seen the chemical results to see if in fact, we're finding fewer and lower concentrations in the effluent and in the corresponding river samples. I know that data has been collected, but I haven't seen that data itself yet.
Another question, do you have any info on emerging contaminant levels where the water has been recharged to an aquifer and then recovered for use?
Yeah, that's certainly an interesting pathway. I can't think of anything off the top of my head that I could spit out in terms of data, but certainly water reuse. There's many parts of the country and parts of the world where water reuse is going to be a necessity. It's already taking place and will take place more in the future. So I think that's something that needs more research, but I don't have anything at my fingertips to show, here's concentrations that were injected, aquifer storage and recovery type of scenarios that I could provide at the moment. But I agree that is an interesting question and a line of research that is worth following.
Are there any pre-treatment requirements imposed on pharmaceutical manufacturers prior to discharging to the sanitary waste stream?
I'm not aware in terms of pharmaceuticals. I think, again, we're not a regulatory agency, so I may be talking maybe kind of on thin ice, but I think there is in terms of solvents. But as far as I'm aware of in terms of pharmaceutical ingredients, there is no pre-treatment to my knowledge anyway. I could be wrong, but that's what I believe.
Do you think that pharmaceutical take-back programs are a viable approach to alleviate the problem, or not? Or what's your thoughts there?
I think it's important to do. And it's really hard to get statistics to say X percent of what's being input into a wastewater treatment plant is coming from people just throwing away and disposing unused and expired medications. I've seen as 10 to 30% as guesses. I still think most of what's being input into a wastewater treatment plant is proper ingestion and use, after prescription. So I think these take-back programs won't solve the issue. You got to start somewhere. So I think certainly throwing things, pharmaceuticals down the toilet is not a good thing to do. It will go right into the wastewater treatment plant. So we might as well tackle the part of the equation that is the simplest. So I at least personally, I'm not speaking for the USGS, but personally I think these things are a good idea because the current, certainly do not want to throw them down the toilet. The current government regulations are saying grind them up, put them with something undesirable like kitty litter or coffee grounds and throw them in the garbage. Now that certainly is a slower path, but personally that prevents misuse and kids accidentally taking medication that might look like candy or dumpster divers for drugs. But again, once it goes in the garbage, a lot of that goes to the landfill, and in many cases the landfill leachate is brought back to the wastewater treatment plant for treatment. So it's more of a circular route, but it's still a potential route. So the current disposal, in terms of throwing the garbage, I'm not sure that really is preventing contamination. It might, but it may just slow things down. So, but long story short, I do think take-back programs are important, but they're not going to solve the issue because most of what we're finding is probably simply to normal use.
Can you recommend sources of toxicity values for these type of compounds?
Boy, that is a great question, but I am not aware of there's some toxicity values out there for some compounds. Some we know nothing about, but a lot of these compounds, it's more the standard tox test. Again, I'm not a toxicologist, so I may be completely off base with my answer. But I think a lot of the effects are going to be more chronic, low-level effects, behavioral effects that may not be picked up on with the standard tox test.
Another question is, are you anticipating that hospitals and retirement homes will have compliance issues at all? Like, has the effluent directly from these facilities been studied, like coming from a pharmaceutical manufacturer?
It's certainly been considered. There's been some research on the hospitals. I'm not sure about nursing home or other types of care facilities, but there has been work done in the hospitals. What I've seen is certainly with the pure influent, that concentrations can be high. I haven't seen as high as what we found with the pharmaceutical manufacturing, but they were high. But because the input is so small compared to the rest of the residential waste, at least the paper I saw showed that once it got mixed, it was diluted, and you really couldn't see the big hospital signature. And that kind of seemed to play out with that one slide I showed. I don't know if I can get my hands on it here really quickly. Let's see if I can find that quickly. Yeah, well, I was lucky, right? First one. So, at least with these 23 sites, really didn't see any difference with these 7 compounds. Again, it may be pushing it to extrapolate to all compounds and all sites. But, hospitals are certainly going to be a source, but in many cases it may be there's such a small portion of the waste that's being treated that they may not be dramatically increasing the concentration levels. But there could be scenarios where that's not the case. You could have say a large university hospital that's in a mid-sized or smaller town, which could have a big input. So, whether they have any sort of regulations coming up, certainly they are a source, and they may be looked at in more detail in the future.
Last question: are you aware of any CEC studies that looked at recycled water use?
Again, I can't think of anything off the top of my head, but this is being thought of much more frequently, so there certainly could be some recent publications I'm not aware of, or ongoing studies that are will have something coming out soon. As I showed in that one slide, it used to be very easy to keep tabs on the whole topic, where there's only maybe 20, 30 papers a year. Now we're talking easily hundreds, and we start looking at all potential journals. Wouldn't surprise me we're in the 500 to 1,000 papers per year, so it's really impossible to keep up on things as I used to be able to. So there likely is something out there. I just can't pinpoint one off the top of my head here.
Sounds good. Well, thank you for taking all those questions. That was a lot of questions. And I want to thank everyone for attending today's webinar that's co-sponsored by the Water Research Foundation. An on-demand version of this webinar, Dana, will be available at our webinar button as well on our website. As a registrant for this webinar, you'll receive a code to access that version of the webinar on demand. It'll be included in an email that you received after this webinar. If you don't receive that code, be sure to contact me at webinar@groundwater.org. All of our previous 2009 webinars are available on demand for free, and all that's required during that is a short registration process. And if you'd like more information about the Groundwater Foundation, you can visit our website at groundwater.org. You can also follow us on Facebook, Twitter, and LinkedIn. And as you see below, I've listed Dana's email there below. And that concludes our webinar. I want everyone to have a great day, and thank you, Dana, once again for your time.